Good morning, Stats fan. How are we doing on this fine Monday morning? A little rainy, a little dreary outside. Weatherman says it's going to get a little colder. I hope you've had a good spring break. I hope everything was going well during your spring break. Hopefully you're staying illness free. Hope everything's going well with your family. Hopefully we're still keeping our social distancing. They say it is making a difference. We want to try to get back to as quick normal as quickly as possible. I miss not having you guys in the classroom. I miss you guys. I wish we had a normal class to go through today. It's 10:15. We'd be sitting in stats class right now. So I wish we were actually sitting here in stats class. What we're going to talk about today is confidence interval. We're going to continue to move through material. Once again, University of Findlay is requiring us to still continue to move through the material, so we will continue to do that. We have 3 more chapters to go through. This one will go pretty quick for us. So it's not a very difficult chapter to go through here. So today we're going to go through what is called confidence interval. And the idea of confidence interval, once again, we're going to take a look at what's happening right now. This is early March, so it's about a month old. Biden led Trump 53% to 42% among registered voters, roughly studied from the CNN polls. This is from CNN. The nationwide picture of Biden start with an edge among voters generally, but nationally polling cannot address the state-by-state electoral votes at this point. So at this point, it was early March, Biden led Trump 53 to 42%. But now we start reading a little bit about the study, and this is where the statistics come in. Okay, the idea of statistics. The study was conducted from CNN via telephone poll, independent research company. Interviews were conducted from April 3rd to 6th among a total of a sample of 1,000 voters, 1,002 respondents. The landline total represents 350, and cell phones were 652. So they sort of define the idea of the sample size, and this is what statistics, some things with respect to statistics that people that deal with statistics do. They have a poll that they're doing. You have a sample, and this is what we've talked about before, and is equal to 1,002, and they broke it down a little bit more. The margin of error, the margin of sampling error for the total respondents is plus or minus 3%. So this is the key idea that you have to look at when you look at numbers. And there's a 95% confidence level, which we will talk about today, in regards to how confident they feel they are. So what we're going to take a look at basically is we're just going to take a look at this margin of error and what it means with our data values here. It always amazed me that when you go through electoral votes and or just elections, TVs will sit there and announce somebody's going to be a winner when there's only 15% of the vote or 20% of the vote that have been calculated. And to me, I've always found that amazing that, okay, there's only 20% of the vote that has been counted. How can you say somebody's won already? Because there's votes that are still there. If there's votes that are still there that need to be counted, they haven't won yet. So, that's where I look at statistics and what they deal with statistics. They deal a lot of statistical analysis in regards to the guessing things, okay, and predicting out. Just like we predict weather with respect to statistics, they also do the election polls with respect to statistics. Now, what this means is Biden, which was 53%. You had Trump, that was 42%. Okay, that's what their poll said, 53% to 42%. That was their sample. They took a sample out. But they want to be able to predict out an entire population. This is just 1,000 people. Now, more than 1,000 people will vote for the presidency. So how do they take a look at these amounts here and predict out? Okay, with only 1,000 people, that's taking a sample, predicting out a population. Well, that's where it takes a look at this error of plus or minus 3%. This is error. So this means Biden is going to receive 50%, they're going to predict out Biden's going to receive 53% of the vote plus or minus 3.7%. So Biden could be somewhere between 56.7% of the vote, or he could drop all the way down to 49.3% of the vote. So you have these two values here that he could be in between. Trump could go from 45.7% of the vote, adding the 3%, 3.7, all the way down to 39.3% of the vote. So what happens here is this error can take the percentages up or down. So if you start taking a look at this, okay, now he's pretty close to the same, or close to being even if you take a look at the bottom value and the top value. So that's what we're talking about here in regards to what statistics do for political elections or anything that we have dealing with respect to predictions. They look a lot of, if you listen to the president, they talk about raw data. We get these raw data values, and if we get these raw data values, we can predict out more and more. And now they're getting the raw data values that they can sit there and predict out more and more and more. The other thing that we talk about here is this 95%, they're 95% confident something's going to occur. That means they're still 5% not confident. So if they're 95% confident, then they're 5% not confident. These are true values. Okay, and that's what we're going to talk about today is a confidence level and a confidence interval in regards to predictions. And once again, they are trying to predict population. They're trying to predict the population by just taking a look at 1,000 people. Now, if you think about taking a look at 1,000 people, you know, statistics can do whatever they want to do. They can bend statistics however they want to bend statistics. Were these people chosen at random throughout the United States? Okay, we don't know that. Okay, were they in a state that was more Trump oriented or more Biden or Democratic or more Republican? We don't know that. Okay, so you can bend statistics however you want to bend them and sort of sway the data that's coming in. Okay, and some people will do that. Now other people, if they are reputable in regards to their polls and their statistical analysis, they're not going to sit there and be biased one way or another. Because if they're biased one way or another, people aren't going to believe their statistics, and if they're not going to believe their statistics, okay, they're not going to go to these people to try to do their statistical analysis and their polls at that point. Now, if we take a look at the notes today, some strange stats today. Average life expectancy of an enemy soldier in a Chuck Norris film, 4 seconds. You're going to get rid of them. The cost of raising a medium-sized dog to age 11, $6,400, okay? Average sized dog, just a medium sized dog, to raise them to age 11, $6,400. Okay, you got all your vet bills, you have all your food that you purchase. And if this is a bigger dog, that's going to get bigger because they eat a lot more food. These are estimates of the population. These are estimates of a population. And once again, if I'm going too fast, hit your pause button, and that will slow me down. A parameter means you're taking taking if we're talking about a population. Once again, parameter deals with a population. What we're going to start talking about today is what is a point estimate. A point estimate. The best point estimate is a specific numerical estimate of a parameter. Okay, you're given an estimate. You go out here to Country Corner. Say I want to do a survey. Okay, I want to do a survey, and I'm going to ask your customers coming in on a monthly basis or every other month, or they come in for their shots, and ask them how much you think you spent just this month in your dog food bills. Okay, then you can also take a look at the medical bills that they have in regards to them going into the vet in that month. Okay, and what you can do is you can get a guesstimate in regards to what they spend on a monthly basis on food, and then you throw in their vet bills, and then you can get a guesstimate in regards to how much they would spend every year on that dog. Okay, if they do have grooming bills, they have to go to get the dog's hair cut, or do they do it on their own? What do they do with their hair? Okay, so we have a specific numerical estimate of about a parameter. So that would be what is called a point estimate. Okay, it's just an estimate at that one point, at that one instance. And you can take, you can ask Dr. Gerber out there at Country Corner Vet and say, okay, can I do this with all your dogs that you have coming in? And just survey the people as they come in regards to how much they spend on their dog. And you can come up with an idea of a point estimate at that point. The best point estimate of the population mean is the sample mean. Okay, you asking all those people out of Dr. Gerber's Country Corner, you asking them a survey in regards to how much it costs them to raise their dog on a monthly basis, how much they spend in dog food, so on and so forth. And you can even make it easier. Say how many bags of dog food do you buy every month for your dog? And then you can go down to Walmart and see how much each bag of dog food costs, or you can just Google it, and you can see how much each bag of dog food costs, and then look at, do they groom their dogs? What's their vet bills going to be? And you can get a good point estimate in regards to the population mean. Because what you're doing is you're calculating a sample mean at that point. You could take 10 dogs, 15 dogs, 20 dogs, and do a sample mean of that, and that would be a population point estimate. It's not going to be exact, but it's going to be close. Okay, so if you take one vet's office, track a medium-sized dog to age 11, find the cost per year. A sample mean is a better point estimator than the sample median and mode. If you take the sample mean, that's a better point estimate than the sample median and mode. Properties of a good estimator. Once again, if I'm going too fast, just hit your pause button. Estimator should be unbiased. Okay, it should not be a person from PetSmart sitting there doing the surveys. Reason why is that PetSmart people are in the job of trying to sell dogs. Okay, so they're not going to sit there and say, this dog, here's a nice small dog for you. Okay, it's a great little puppy that loves attention and will be very great with any kids that you have around your house. But this dog's going to cost you $10,000, it's going to cost you $2,000 a year. They're not going to do that because they want to sell the dog. If somebody sits there and says, this is going to cost me $2,000, $2,400 a year, that's $200 a month. I don't know if I want to buy that dog or not. So it shouldn't be anybody that's going to be biased in regards to this. The estimator should be consistent. As sample size increases, the value of the estimator The value of the estimator approaches the value of the parameter estimated. So you should be consistent, and once again, as the sample size increases, the value of the estimator will approach the population mean. Once again, this is law of large numbers. The bigger your sample size, the more you're going to get closer to your exact value that you want. Estimator should be relatively efficient estimator, and the best estimator has small variances. They will have small variances. Going back to a problem what we've done before, average value of a registered vehicle is 8 years, 96 months. Assume the standard deviation is 16 months. If a random sample of 36 vehicles is selected, find the probability that their mean age is going to be between 90 and 100 months. Okay, their mean age is going to be between 90 and 100 months. Okay, so what we have here is we have a population mean of 96 months. Standard deviation is 16. We have a sample size of 36. And we want to know what is the probability their mean age is between 90 and 100 months. So what we have here is our bell-shaped curve again. What we have to calculate is a z-score for our 90 and our z-score for 100. Now if you remember back using our central limit theorem, how we find our z-score, we have 90 minus 96 divided by our standard deviation, 16, divided by a square root of 36. And then we have 100 minus 96 divided by 16 divided by a square root of 36. Once again, we are just looking at our central limit theorem. So go ahead and calculate them. See, -6 divided by 4 times 6. Divided by 16. 6. -2.25. Then we have 4 divided by 16 times 6. We have 1.5. So we have our values. We have our 0 here, we have 1.5, 0 here, and -2.25 here. So we want to calculate the probability, which means we need to calculate the area. So go to your z table, find these two values that correspond to these z values. can't find my Z table. Sorry about that. Couldn't find my Z table. Let's see here. Negative 2.25. 2.25. We get 0.4946 for 2 point. I'm sorry. I got the wrong value. 2.25, 0.4878. And then 1.50, we have 0.4332. And what do we have to do with these to calculate the total area? We have to add them. So we have 0.4878 plus 0.4332. We add them together. Plus 0.4332. We get 0.921. So if we look at our question here, what's the probability that the mean age is between 90 and 100 months? Well, we have 92.1% probability that the age of this vehicle is going to be between 90 months and 100 months. Once again, this is a review of what we've dealt with before. This is the percent probability that the mean sample is between 90 and 100 months. So we have 92.1% chance. But what we can also state is the percent confidence that the mean lies between 90 and 100 months. We are 92.1% sure that the mean age is going to be between 90 and 100 months. If I took the mean of all these 16 vehicles that we have here, I'm 92% confident that's going to occur. Now, if you're 92% confident something occurred, that's pretty confident. Yeah, that's pretty confident. If you have $100 and you're going to bet on something, would you bet on something with your $100 that if you win, you're going to get $100 back? Would you? You're 92% sure that's going to happen. Would you do that? Well, this is going to be the interval estimate. It is an interval or a range of values used to estimate a parameter. This may or may not contain the value of the parameter being estimated. So of these 16 vehicles, I'm 92% sure that their mean age is going to be between 90 and 100 months. Okay, that gives me a range of values. That means I'm 8% sure, not sure about all this. So this interval estimate is a boundary values of values here. We have a confidence interval. It is the probability that an interval estimate will contain the parameter. Using large enough numbers, law of large numbers, are selected and the estimation process on the same parameter is repeated. All good experiments are repeatable. That's why you write down a process in regards to how you did that, because if somebody else would want to repeat that process, they should come out with the same results. So it's a probability the interval estimate will contain a parameter assuming a large number of samples are selected and the estimation process on the same parameter is repeatable. Confidence interval. And once again, if I'm going too fast, just hit pause. A specific interval estimate of a parameter determined by using data from a sample and by using specific confidence intervals a level of an estimate. So this is a confidence interval. It's very similar to an interval estimate. These two things here are very similar to each other. It's a specific interval estimate of a parameter determined by using data from a sample, by using a specific confidence level estimate. What we will be doing, we will have a sample size of size n. We will calculate the interval using z-scores to illustrate confidence level that the population mean will be somewhere between these two values. So we're going to use a sample just like we did on this first page here. Okay, we're going to use a sample and we're going to use a specific confidence. In that specific confidence, we're going to give two boundary values that we are 95 or 97 or 98% confident that the actual population parameter, which is a population mean most of the time, will be between these two values. Most confidence intervals or levels will be 90%, 95%, or 99% confident. Now, if you're 99% confident something's going to occur, you're pretty confident about that. The survey that we did at the beginning was only a 95% confidence level, and each confidence level will vary. The population average for a salary of teachers in Ohio is 41,000 with a standard deviation of 1,500. What is the upper boundary and lower boundary for the salary that would encompass a 90% of these salaries? 90% of these salaries. This is a problem what we have done already. We have a population mean is $41,000. We have a standard deviation of $1,500. So if we take a look at how we turned this problem or what we did before, we did this. Here's our middle. And here's our two outside values. We want the salaries for the 90% of the middle here. Okay, we want what is these upper and lower boundaries for these 90% of the salaries in the state of Ohio. And what we did before, okay, we had our mean, we had our standard deviation. Well, we had to calculate it, we had to calculate our z-value. So we had to determine these z-values that we have here. And we moved this into 45% and 45%. And this area here is 0.4500. This area here was 0.4500. Then we took a look at the body of our z-table. Here's our body, and we found the value that's closest to 0.4500. Well, if you remember, we had two values. You had 0.4495 and 0.4505. You're halfway in between, and we decide, well, which value should we use there? Well, the value that we should use is 1.65. So we came down to values here of 1.65 and negative 1.65. So with these z values, we were able to calculate a value is our mean 41,000 plus our z value negative 1.65 times our standard deviation of 1,500. And then 41,000 plus positive 1.65 times 1,500. So pulling out the calculator, 41 plus a negative 1.65 times 1500. Let's try that again. 41,000 plus negative 1.65 times 1500. That's better. 38,525. And 43,475. These were our boundary values that would encompass 90% of our salaries. 90% of the salaries in the state of Ohio are going to be somewhere between 38,525 and 43,475. That is 90% of the salaries. And this is the type of problem that we've already done. Now, if we remember, our standard deviation for a sample mean is equal to population standard deviation divided by square root of n. So if we take a look at this right here, if we make a population, if we take a look at a sample population mean and a sample population standard deviation, what this converts into is our mean plus our z-value standard deviation divided by square root of n. And this is what we'll be utilizing for the rest of our problems. 40 teachers are chosen from the population of Ohio teachers. Okay, 40% or 40 teachers are chosen from the population of Ohio teachers. Their mean salary was 41,000. Population standard deviation was 1,500. Find the confidence interval for a confidence level of 90%. So what we have here is we have a sample of 40 teachers. We have their mean salary is $41,000. Their mean salary, so that's a sample mean. Their standard deviation is 1,500. And we want to find a 90% confidence level of these values here. So how this changes is it does not change much. Okay? All it changes is now we're looking at a sample mean. So we're still looking at dealing with 90% from here to here. 90% from here to here. This area is still 0.4500, 0.4500. But our z values we now know are negative 1.65 and positive 1.65. So if we look at this confidence interval, once again, we are trying to predict out our population. We can take our x bar plus our z value, standard deviation divided by square root of n. Once again, now we're, as we talked about before in the earliest one, our sample size is now 1, rather than our sample size is now 40, rather than the sample size is just 1. So if we take a look here, we have 41,000. Plus our z-score, which is negative 1.65, times our standard deviation, which is 1,500, divided by the square root of 40. And then 41,000 plus 1.65 times 1,500 by the square root of 40. So if we take a look at these values here, 41,000 plus negative 1.65 times 1,500 divided by square root of 40. We have 4608.66. Delete. We have 41,391.33. Here's our two values. What we are able to determine, once again, a confidence interval estimates our population. What we have here is two values that we calculated. With our data that we just calculated and determined, we are 90% confident population mean for teachers is between 40,608 and 41,391. This is what allows us to predict our population. Okay? With this confidence interval, we're 90% confident that our population mean is going to lie somewhere between those two values. We talk about a confidence interval. Once again, confidence intervals typically 90, 95, 99. And alpha level is the amount of area in the two tails. So that this area here is 0.90 or 90%. This is your alpha value, this is your alpha value. Well, we have two different tails, so this is 10% divided by 2 or 5%, and this would be 5% also. So my area here, alpha, is going to equal 0.05, and this alpha here would be 0.05. That's your area in your two tails. And once again, our confidence level for the population mean is calculated by our X, our sample mean, our Z for the confidence interval, standard deviation divided by square root of n. So we have minus that, and then we have plus that. So we can guesstimate a population mean is going to be somewhere between these two different calculations, which is what we did up here. This is our population mean. This is our Z value, standard deviation divided by square root of n. Now, what I've given you here is a table. You do not have to memorize this table, but you can utilize it to do your homework. The main thing is to remember, or to look at, if I have a 90% confidence interval, my Z value is 1.65. For a 95% confidence interval, 1.96 and 2.58. You do not have to draw a bell-shaped curve anymore and go to your Z table to be able to calculate these values. You can utilize this Z value for this confidence interval. This value right here are these values right here. Don't worry about the last page of notes, but we'll go over them tomorrow, along with some additional problems in regards to Z values. We'll go over them tomorrow. So this should get you going on your homework. I got you some homework there. I got you solutions to the homework also, so you can refer back to your solutions or your homeworks. Once again, get a routine of how to get through the class, or get yourself a routine in regards to material and what you're doing in your schoolwork. Once again, we'll go over some additional problems tomorrow, and we'll go over the other page of notes that we have here tomorrow also. Stay safe, keep your social distancing, talk to people, enjoy some warm weather while we still have it. Might be a little rainy out there, but enjoy some warm weather. Other than that, I have nothing else for you. If you have any questions, feel free to comment, ask me, email me any type of questions that you might have in regards to this material here. Other than that, I'm out for the day. Adios. See you tomorrow.